Hello and welcome to this course on convex optimization. In previous lectures, we've talked about quadratic programs and linear programs. In this one, we're going to cover a bunch of topics related to quadratically constrained quadratic programs. First, we're going to introduce what a QCQP is, and then we're going to visualize the feasible region of a QCQP on MATLAB. Then we're going to see three types of problems, which are QCQPs, and we're going to learn some tricks on how to solve them. So without further ado, let's get started. So in this one, we're going to talk about QCQPs, which stands for Quadratically Constrained Quadratic Programs. So in lecture 6, the previous lecture, we talked about quadratic programs, where we introduced what a quadratic program is, reformulated a quadratic program in matrix form, and gave an illustration. And finally, we've seen how to solve a quadratic program using the quad-prog function of MATLAB. In this lecture, we're going to go in depth into a broader class of problems, which are QCQPs. I'm not sure if in the last lecture we stated that the QP, so let's say this is a QP, and this is a set of all QP problems. I'm not sure if we stated the following. So any LP is a particular instance of a QP. It's easily seen by setting P equal to 0. So if we say that this matrix is 0, then we get an LP, right? And hence, LPs are particular instances of QPs. Well, in a very similar way, we're going to see that there is a broader class called QCQPs. So that's why we didn't give many examples in QP, because all examples that will be given in QCQPs also include QPs. So what is a QCQP? We're going to minimize, since it's a QP, we're going to minimize a quadratic function that is of the form, we've got a quadratic cost function, x transpose px plus q transpose x plus a constant r, right? Now, your constraints is what's going to make a difference. So subject to what? We've still got the affine constraint of the QP, right? This guy is still here, as well as the cost function. It remains unchanged. However, your linear inequalities become now quadratic inequalities. That is, you've got m quadratic inequalities. Quadratic, hence they follow the same structure as the cost function. So the difference is right here. X transpose PIX. If you've got m inequalities, you've got m pi matrices, P1 till Pm, plus Qi transpose X plus Ri, less than or equal to 0. And if we've got m constraints, then I should be spanning 1 till n. So now you've got m matrices, P1 down till Pm, and vectors, Q1 down till Qm, and m constants, R1 down till Rn. So that we distinguish those inequalities from the cost function, we usually give a nod here, P nod, Q nod, and R nod. And again, as we said in the previous lecture, we've got a half here showing up due to the gradient. So I'm going to insert a half right here. You can do without it, but I'm going to insert it just to be consistent with MATLAB. So yeah, this is a QCQP. And to see QP as a particular instance of QCQP, all you have to do is set your PIs to 0. So if all my PIs are equal to 0, then I get a QP problem. Okay? So what are we doing really in a QCQP? We're minimizing a convex quadratic function, that's the cost, over, of course, a feasible region that is defined by the constraints. But how do they show up graphically? We said previously that in a QP, this green region right here forms the so-called feasible set P. And this region is geometrically a polyhedron, since it's an intersection of half spaces and hyperplanes, right? Well, a QCQP is going to generalize that. It's going to say that oh, now I have quadratic inequalities. And what do quadratic inequalities form? They form ellipsoids. So each quadratic inequality, each one of those is an ellipsoid. Okay? So maybe if I've got two inequalities in 3D, let's say x lies in 3 dimensions, so my first ellipsoid is here. This is for I equal to 1, and for I equal to 2, maybe I've got an ellipsoid that is the green one. And one thing worth noting, so that we have an ellipsoid, all your PIs should be symmetric and positive definite. So, in other words, all your PIs, of course, including P0, because that's already mentioned in the quadratic program formulation, you said that P should be in S plus N. Well, now all your PIs should be in S plus N. I don't know for you, but for me, I'm a visual person. I don't like how this rubbish looks like, so I'm going to open MATLAB. I'm going to write a script to draw us the feasible region, which is intersection of ellipsoids. So I'm going to go here and create a function, draw QCQP Feasible Region. I'm going to open this. So this is what we've got right here. So before I decide on the input arguments, it's really worth shedding light on the ellipsoid function of MATLAB. So if I hit F1, ellipsoid generates an ellipsoid. So all it does is that it takes those parameters and generates a surface mesh described by 3 n plus 1 by n plus 1 matrices, enabling surf to plot an ellipsoid with centers xc, yc, zc, so this is the center of our ellipsoid, and semi-axis of length xr, yr, and zr, where n is the length of the mesh grid. Now, I'm going to use this function to generate multiple ellipsoids and plot them. So with that being said, my function should naturally take as inputs the centers of the ellipsoids. So each one of those is a vector where each entry of the vector is a center of one ellipsoid. So let's say those vectors are of size 3, each one. So I should be able to plot 3 ellipsoids. Not only that, I'm going to take theta, which is a rotational angle of the ellipsoid. We know that an ellipsoid could be rotated. And I'm going to take also the length of the semi-axis, min and their max. Output, I really don't need any output, so I'm going to remove this. And over here, I'm going to run a loop. So in this loop, I'm going to pass by all the elements of the vectors. So note that if you want this to be more concrete, you can type here blocks of code. All your inputs should be of same length. Else, throw an error. Okay? Now let's assume that all my inputs are of the same length. Each entry corresponds to an ellipsoid. So I'm going to return a mesh grid of the kth ellipsoid. Okay? According to the documentation, this is xk, yk, zk, and over here, we're going to take r min k, r max k, and the z, I'm going to set it as a constant. So r min k, r max k, and a constant, let's say 5. And a mesh grid length of 30. So 30 points per mesh grid. Note that documentation is telling us enabling surf XYZ. So right now you're ready to run the surf. So surf XYZ. And since we've got rotational angles right here, I'm going to return the surface. So this is xk, means the surface of the kth ellipsoid. I'm going to rotate it about the z-axis, so 0, 0, 1, by a value defined by the kth entry of theta. Okay, so documentation of rotate, here you have it. So it rotates the object h by alpha degrees. So this defines h and alpha, and what is direction? it is a 2 or 3 element vector. In our case, it's 3 because we're going to plot in 3D, that describes the axis of rotation. So since I defined it as 0, 0, 1, means I'm rotating about the z, and that's basically it. You can label your x-axis as such, y-axis, and the z-axis, right? Hold on each time we plot a new and what else? We can give a nice color map. So color map, I prefer the winter color map. And what remains is to define our inputs. So I'm going to create another script, call it main, feasible. And my script, I'm going to clear all and CLC. And the x values of the centers, I'm going to pick them as such, 0, 2, 5. The y, I'm going to pick them 0, 2, 6. And the z, be careful, I'm giving them the same dimensions, because if I want to plot 3 ellipsoids, each vector should have 3 values. So here I'm going to rotate by 30, 60, and 90. The Rmin, I'll give 1, 2, 3, and an Rmax, I'll give. Also, Rmin should be less than Rmax entry-wise, right? And last but not least, I am ready to run this function. So draw. Rmax is defined here, min is here, theta is here, z, y, and x. Okay, let's run. We've got an error. What is the error? The error is at line 6, and it's saying index exceeds matrix dimensions. So this is a point, this should be a comma. Sorry about that. Run again. And there you have it. And where exactly is the feasible region? It is, in fact, the intersection of all ellipsoids. So is there an intersection here? Let's zoom in. There is no intersection with those 2 ellipsoids. As you can see, there's an empty gap. There's a gap, so there's no intersection. And right here, we can see that those 2 ellipsoids are intersecting, hence forming a non-empty feasible region. They're intersecting, to be precise, in this region right here. Okay, let's try to intersect all ellipsoids. So I'll set this to 3 maybe, run. There you have it, looking good. Let's rotate this even more. Let's put this as a 90. Run. Let's put it as a minus 90. And there you have this ellipsoid intersecting this. So this is the y-axis at 8 for this ellipsoid. This ellipsoid is centered at, all ellipsoids are centered at 0. Look at the z. So this is the x and the y. So I'm going to shift this ellipsoid back here. So I'll reduce this y to, let's say, 1 and run. There you go. All 3 are intersecting, hence forming a non-empty feasible region. Okay? Just wanted to show you how to visualize on MATLAB the QCQP feasible region. Okay, so far so good. Let's see some interesting applications of QCQPs. One really nice application and easy to solve. You don't need to know Lagrangian multipliers, duality, all this kind of theory. You don't need to know. You can solve such a QCQP without this knowledge. You could minimize a linear function over a centered ellipsoid. This you can easily do. So now, let's formulate the problem. First, let's minimize a linear function. So the following is a linear function. C transpose x, right? We're minimizing over x, subject to a centered ellipsoid. So how do we represent mathematically a centered ellipsoid? We know that a quadratic form as such reflects a centered ellipsoid, where A is a symmetric positive definite matrix, of course. And to define the boundaries of the ellipsoid, it's bounded by 1. You can bound it by r, right? Or any number you want, but for simplicity, we're bounding it by 1. So how can we solve such a problem? say you're given this problem, you don't know Lagrangian multipliers, you don't know the duality theory of convex optimization. How do you solve such a problem? Note that the constraint here could be decomposed as follows. So the x transpose ax, you could write x transpose a half x is less than 1, right? Because we all know that the square root of a matrix is defined as follows. A half times a half is a. And what is a half? It's not entry-wise square root, no. It's the square root of a matrix. It's a matrix that, if multiplied by itself, it gives the original matrix, okay? So if we note the following of the constraint, we could take a change of variable as such. So we can pick this part to be a vector y, right? So this means we're doing a change of variable. So y is a half x, right? This means that my new problem is the following. So this guy, with this change of variable, we get the following new problem. So we're minimizing now over y, not x. So if this part right here is a y, then what is this? Let's write y transpose. Y transpose is a half x transpose. Now using the circular property of the transpose, we get x transpose a half. And since a is symmetric, and so is its square root, so we get x transpose a half. Okay? So this guy right here is y transpose. So the constraint is nothing other than y transpose y is less than 1. Now what does the cost function become? Since we need to express x as a function of y, we've got y as a function of x, right? Let's multiply on both sides by the inverse of a half. A, let's denote it by a minus half. Y is equal to a minus half x, right? And a minus half times a half is the identity matrix. So we're left with I times x. And I times x is x, right? So here we go. We got x as a function of y, which is a minus half times y, right? So replacing this in the cost, we get c transpose, which is a constant, times all this guy right here. I'm going to plug it to replace x right here. Now to reduce the notation, let's denote another constant vector. C bar transpose is c transpose a minus half. Why am I doing this? So that we can see that we still have a linear cost upon this change of variable, right? If we plug this is a c bar, huh? If we plug this here, we get this cost function, this problem. So minimize over y, c bar transpose. I did a mistake right here. This guy should be a y, right? Not an x. So upon this change of variable, it's not a change of variable because neither c nor a is a variable, right? So it's just readjusting the problem, if you will. So c bar transpose y subject to y transpose y is less than 1. And why did we do this reformulation? Why is this better than this? Okay, so how do we solve this problem without having to go to the theory of Lagrangian multipliers? Let's first note that minimizing a cost is the equivalent of maximizing the negation of the cost. That's 1, right? So there's nothing wrong with writing the following. So here we have a minus sign, just to say, oh, we're maximizing the negative. So we're minimizing the original cost function. And another thing that we should all know at this level of convex optimization is the Cauchy-Schwarz theorem. That's a really important theorem or inequality, let's say. It's an inequality. And it tells us the following. I need only this part right here. So it's telling us here that if we've got u and v, which are arbitrary vectors in a vector space over a field F, So we've got this inequality, which is the Cauchy-Schwarz inequality. It tells us that an inner product between two vectors is lower bounded by the product of their norms. And equality holds only if u is a multiple of v. So with that being said, I'm going to write this over here. So Cauchy-Schwarz is basically telling us x transpose y is always lower bounded by the norm of x times the norm of y. In our application, since we're working with real numbers, if you're working with complex numbers, you can easily reformulate it to real numbers. We'll see that later on. So the norm. So what is the norm in our case? Let's work with the L2 norm. X transpose times y is always lower bounded by the square root of x transpose x times the square root of y transpose y, right? Actually, let me replace this x with a c bar because that's what we exactly have, right? So I'm going to erase my x everywhere. I'm just going to replace it with a c bar. And what value of y should I choose so that this quantity is maximized? And actually, we should have replaced x with a minus c bar transpose because this is what we've got. So if I put a minus right here, a minus goes here, a minus goes here, and minus times minus is a plus. Actually, the minus in a norm is also removed, right? Because it's a norm. And yeah, this is what we exactly want. So this guy right here. Aren't we maximizing this quantity? Isn't this our cost function? Yes, it's over here, exactly. So when is this guy maximized? It's when we hit this upper bound. And when is this attained? It's when u and v are multiples of each other. That is, when you choose y is a multiple of minus c bar. So if I go ahead and choose my y, let's call it y star, because this is the optimal y. This is the y that maximizes this or minimizes this, right? So when it's equal to alpha, where alpha is a scalar, so alpha is an r, times the vector, minus c bar, which is minus alpha c bar. So there you go. This is an optimal solution, but we still have to figure out alpha. Okay, it's a multiple of c bar, good, but what is alpha? You can't leave a free parameter hanging as such. You didn't solve your problem. You're halfway there. So what is alpha? It's defined by your constraint, right? If I go ahead and replace it in the constraint, I'm going to get this. So if y star transpose y star is equal to minus alpha c bar transpose times minus alpha c bar. This guy is equal to, since alpha and alpha are scalars, you can extract them outside, and a minus times a minus is a plus, so you get an alpha square times c bar transpose times c bar. Okay? So this guy should be less than 1 according to the constraint, right? So this is going to allow me to choose my alpha, or at least bound my alpha. This tells us that alpha squared should be less than 1 over c bar transpose c bar. And alpha here is positive because we know this guy right here is all negative, so we're going to choose alpha less than the plus. Taking the square root of all this, we get the square root of c bar transpose c. So alpha at least should satisfy this. However, how do we choose the best alpha? It is right back here in the cost. So remember, we're maximizing this cost. So if I replace y star in the cost, replace y star back in the cost, what do I get? Minus c bar transpose times, replacing y star, we get minus alpha c bar. A minus and minus is a plus, and alpha is extracted outside. So this becomes alpha c bar transpose times c. So this is your cost at the optimal value, at the optimal y, right? So what should alpha be to maximize this? you should choose alpha as maximum as possible. So alpha should be equal, not less than. It should be equal to this guy right here. This guy is positive. So the higher alpha is, the higher this cost is, and the more you are able to lift minus C bar transpose Y, right? So choosing alpha to be this upper bound, we get 1 over square root of C bar transpose C bar times what's left here. So C bar transpose C bar, right? Now, since C transpose C is a constant, is a scalar, so is the square root, right? So we can, cancel this with this, and we're left with a square root of C bar transpose C bar. So this is your optimal cost. Now, what is the optimal value? Y star is minus alpha C bar, right? So this is equal to, replacing this alpha right here, the one in green, the upper bound, we get 1 over square root C bar transpose C bar, and we're left with a C bar, and don't forget the minus, so minus. This is Y star, no free parameters, you expressed it as a function of parameters given in the problem. Don't forget C bar is equal to, this is your C bar transpose, so C bar is equal to C transpose A minus half all transpose, which is, using the circular property of the transpose, we get A minus half C. So this is your C bar, and let's replace it right here. So Y star now becomes minus 1 over, this is C bar, and C bar transpose was originally given as C transpose A minus half. We get a square root of C bar transpose, which is this guy. So C transpose A minus half. C bar is this guy. So A minus half C times C bar, which is again this. A minus half C. Note that A minus half times A minus half is nothing other than A minus 1, the inverse of A. So that being said, we get that Y star is minus 1 over square root of C transpose A minus 1 C times A minus half C, right? And to go back to the X domain, which is originally the problem we had right here, we need to use this, right? So we've got Y star. If we plug it here, we are able to get our optimal X star, which is what we need. So we need this equation right here. X star is A minus half Y star, and Y star is all this. Plug it here, we will get the following. So minus 1 over all. This is a constant, so I'll keep it to the extreme left. And I'm going to bring this A minus half. I'm going to bring this A minus half next to this A minus half right here, where together they form an A minus 1 times C. So this is the optimal solution to your problem. Now, what happens if this matrix is not invertible? First of all, this solution does not exist, right? You cannot write A minus 1 since A minus 1 does not exist. So what's going on? Let's try to write the cost function, which is minus C bar transpose Y, right here, or C bar transpose Y right here. Let's try to write it. So C bar transpose Y at the optimal solution is, we said that C bar transpose is this guy, so C transpose A minus half, right? And the Y star is all this, so I'm going to copy it here. So 1 over square root of C transpose A minus 1C times, this is my Y star, A minus half C, right? This guy is a scalar. This gives us, since this is a scalar as well as this, we can cancel out the square root down there, and we're left with a square root of C transpose A minus 1C. So this guy is P star, the optimal cost. We use this notation right here. So F0x is equal to P star at the optimal x. So what happens if A minus 1 does not exist. So let's try to see stuff at the limit. So A, using eigenvalue decomposition, can be written as P, D, P minus 1, where P contains the eigenvectors in its columns, and D contains the eigenvalues in its diagonal entry. D is diagonal, right? So once you invert this, A minus 1, you could write it as P, D minus 1, P minus 1, right? And when an eigenvalue is going to 0, A minus 1 is exploding, right? It's going to infinity, or at least some of its elements is going to infinity. And hence, this cost is also going to infinity. And we say that the cost function is unbounded below. Okay, so this wraps it up for this problem, namely the minimization of a linear function over a centered ellipsoid. Now, what happens if the ellipsoid is not centered anymore? That is, we're still minimizing the same cost, right? But this time over a different constraint. Now, minimize the same problem right here. So let's refer to this problem as P1. So P2 would be P1 plus an uncentered ellipsoid. So what happens here in this problem? So you can have the same cost as we said, since we're still minimizing a linear function, but this time subject to a general ellipsoid. That is x minus xc transpose, where x and xc are both vectors, right? A x minus xc. Note that xc contains the coordinates of the center. Is there anything we can use from the previous problem to help us solve this problem? Well, with a simple change of variable, you can boil down to the same problem as we had before. So if we note that the same way as in the previous problem, in particular, and the same way we decompose a into a half times a half, the square root of a, we're going to use the same trick. That is x minus xc transpose a half multiplied by a half times x minus xc less than 1. If you choose this guy to be y, and hence this guy is y transpose, guess what? You get the same problem in y as before. See how important this change of variable is? So minimize with respect to y, c transpose x subject to y transpose y is less than 1. Now we still need to replace this x as a function of y. Let's do this. We've got y is a half x minus xc. That is expanded first, then get this guy to the other side. Y plus a half xc is equal to a half x. Now multiply both sides by a minus half. So you get a minus half y plus a half xc is equal to a minus half times a half times x. Now those two cancel out to give us the identity matrix, which leaves us with x. And there you go. Your x now is the left-hand side. Try to expand it. A minus half y plus, again, a minus half times a half is identity, which leaves us with xc. So we can say that my x is equal to xc plus a minus half y, right? Replacing this in the cost so that we get a problem in y, you get c transpose times x, which is this guy, c plus a minus half y, subject to the same constraint, y transpose y is less than 1. Note that this cost function right here, we could expand it as such, so c transpose c plus c transpose a minus half y, subject to y transpose y is less than 1. Now, you're minimizing this cost as a function of y. Therefore, this guy is a constant and does not affect the minimization. And hence, we can get rid of it. So we could omit this guy and just focus on this, right? So we're minimizing this, and hence, the final problem we're trying to tackle is this. Now, in a very similar manner as before, you can choose this guy to be C bar, right? So that you have the same exact problem. But of course, in a different X domain, because X is now this. So once you get a Y star, you get this X. So what is your Y star right here? It is the same exact one as here. Namely, it is this one, because you're solving the same problem in y. So we're going to copy this one in P2, our new problem. So my y star is minus 1 over square root C transpose A minus 1C times A minus half times C, right? Now to get x star, I need this equation right here, right? So this one. Let's copy this so that we get x star. So x star is xc plus A minus half y star. Now replace the y star right here, you get xc plus A minus half all this guy right here, which is minus. So this minus goes out here with everything inside, and hence you get xc minus this guy's a scalar. So push it out here. A minus half twice, leaves us with A minus 1 times c, right? And there you go. This is your solution. And what do we notice? We notice that the solution of P1 is embedded here for xc is equal to 0. So in other words, it is this part over here. This is the solution for the P1 problem, for the centered ellipsoid. Okay? And of course, in the same reasoning as we did previously, if A has a 0 eigenvalue, the problem is unbounded below. What we've covered so far is a definition of a QCQP in general. Then we solve two problems. Both aim at minimizing a linear objective function, but each one is subject to a different constraint, in a sense that P1, the first problem, minimizes a linear objective function subject to a centered ellipsoid, whereas P2 is subject to an uncentered ellipsoid. Now we're going to see another similar problem, but we're going to modify the objective function. That is, our aim is to minimize a quadratic cost function subject to a centered ellipsoid. Now the uncentered one is trivial after that, as P2 was trivial when you know what P1 is, right? So let's call this P3, minimize a quadratic function over centered ellipsoid. Okay, so since it's a quadratic function, then a cost function should look something like this, subject to a centered ellipsoid. Again, we're going to use the same trick, that is decompose A into square root as follows. Then we're going to choose this part to be y, and hence this part is a y transpose. So the problem becomes as follows. And now we need to express the cost function as a function of y. So we're going to use this, y is equal to a half x, and multiply by a minus half on both sides, we get x is a minus half y. So exactly the same as P1 and P2. Now we're going to replace this in the cost, we get, so if this is replaced here, we get minimization over y of y transpose a half y subject to the same constraint. So here, we've got some arguments to do. So note that the cost function is still quadratic in y, right? And now we're minimizing over the unit ball. And if we're given that A is positive definite and B is positive semi-definite, so if we're going to call the central matrix C, so if this guy is C, matrix C, you can simply write it as follows, transpose Cy less than 1, right? Here we're going to write between parentheses, C is a half, B a half. So those matrices are given, right? They're formulating the problem. So what is the y that minimizes my problem? So since C is a matrix, then y transpose Cy could be chosen to reflect an eigenvalue. So in that case, let me show you what I mean. So an eigenvalue, using the definition of an eigenvalue, is defined as follows. So CV is equal to lambda V, where V is the eigenvector and lambda is the corresponding eigenvalue. Well, what happens if I do this? V transpose CV, multiplying by V transpose on both sides, lambda V. And since lambda is a scalar, you can extract it to the extreme left, and hence we have lambda V transpose V. Now, eigenvectors could be made such that their norm is 1, and hence this guy right here is equal to 1. just scale the corresponding eigenvalue, and hence the eigenvector becomes of norm 1. And so the following could be satisfied. Now, why am I writing this? So if we denote lambda 1 greater than, lambda 2 greater than, down to lambda n, those are the ordered eigenvalues of C. And we just saw right here that this inner product, V transpose CV, which is of the same form as Y transpose CY, could be seen as an eigenvalue if you choose Y to be an eigenvector. So since we're minimizing, we want to choose the smallest eigenvalue, lambda n, right? So if I choose Y to be the eigenvector corresponding to the smallest eigenvalue, call it Vn or Vmin, right? In that case, your lambda n could be denoted by lambda min. Then you just minimize your cost function without having to look at your constraint. We'll talk about the constraint just a bit further. Just for the moment, pretend that the constraint doesn't exist. So naturally, your unconstrained problem would be the following. If y is equal to v min, then y transpose cy is v min transpose cv min. And using this, you get lambda min, which is the minimum possible, right? Now, if we look at the constraint, we have to be careful. Since y transpose y is less than or equal to 1 and not equal to 1, so y transpose y could be made less than 1. Here, all this assumes that the norm of y is equal to 1, right? As we said here. But what happens if really the y that has to fall in the feasible region, i.e. the unit ball, has a norm less than 1? So what happens in this case? You could actually choose a y is equal to 0, the 0 vector, and hence the minimum of the objective function is 0, not necessarily lambda min, which is not necessarily 0. So what is the argument here? The argument is as follows. So if lambda min is less than, so if the cost attained by the minimum eigenvector is less than that attained by y is equal to 0 and hence 0, then the solution is simply v min, the minimum eigenvector, right? Else, if lambda min is non-negative, then I have a better minimum, which is the 0, since it attains 0 as objective function and not something positive, right? Which is lambda min. So this is simply the solution to my problem. This is the v min of matrix C, which is in turn the matrix A half B A half, right? As such. Perfect. So far we've covered a lot of stuff. This is all the basics you need to know on QCQP. Of course, in future lectures, we're going to see more problems on QCQPs. In the next one, we're going to talk about second-order cone programming. That is a broader class of convex optimization problems. It will include QCQP as a particular instance. So if we remember this diagram right here, so SOCP is going to lie on top of that, okay? SOCP is going to include QCQP and in turn, which includes QP and LP. So that is it for this lecture. I hope someone out there found this useful. Again, please subscribe to my channel. Leave a comment if you think I went wrong somewhere or you need more clarifications or something. You have any sort of question, feel free just to comment. I read all the comments you guys post. I'm really happy for that. It really means a lot. So if you want this channel to keep progressing as it already is doing, please hit the subscribe button. Thank you so much, and I'll see you then.